in chapter 8. We're just going to go through kind of beginning to end. This is not going to be all the details, just hitting the highlights here. We talked about solids, liquids, and gases. And we looked at the difference. What did I write? We looked at the difference between the amount of kinetic energy and the amount of intermolecular forces present in these states of matter between the molecules. So we said gases have the highest amounts of kinetic energy. Solids have the lowest. The molecules really aren't moving a lot. They might be vibrating amounts of kinetic energy. Liquids have some in the middle. They're moving, but they also have a lot of intermolecular forces. Gases, those particles are not interacting a lot. They're moving so fast that they don't have time to interact. So lowest amounts of intermolecular forces, IMF. And solids, those molecules are sitting next to each other. So they have the highest amounts of intermolecular forces. Okay, they kind of look like this, the way we draw them, at least. So lots of intermolecular forces not moving around. We said gas particles, they are just zooming by one another. Lots of kinetic energy, not interacting. Liquids obviously have some intermolecular forces. More than gases, less than solids, okay? Then, after we defined these things, we talked about phases, changes between the phases. So like melting, evaporating, something condensing from a gas to a liquid, freezing. So we gave different like delta H values. We said we can identify each of these reactions as exothermic or endothermic. So if something is going from a gas to a liquid or a liquid to a solid, are these exothermic or endothermic processes? Are these releasing heat or absorbing heat? Do y'all remember? These would all be releasing heat. So these would be a negative delta H, okay? To slow down those particles and bring them closer and closer together and interact them more and more and more, they have to release energy, which is heat as a form of energy. So negative delta, these are all exothermic, okay? And then vice versa, if something is going from a solid to a liquid or a liquid to a gas, so melting, evaporating, we said these are endothermic. They're absorbing heat. Positive delta H. Okay. So again, this is just a quick synopsis of this. Questions on that? Okay. The next thing we talked about were intermolecular forces in detail. Okay. So we said there were three main kinds that we talked about: van der Waals, and then we talked about, we said this was the weakest kind, by the way. We said van der Waals, they occur in all molecules, but if a molecule is nonpolar, by the way, I've had like something in my throat all morning. So if I'm just like hacking up a lung, I'm sorry. It's like not going away. For nonpolar molecules, van der Waals is the strongest. Okay, so these are the strongest forces for nonpolar molecules. And then if you're looking at a group of nonpolar molecules, we said molecules with larger surface area are going to experience more van der Waals forces. So for example, I'll just say the larger surface area equals more van der Waals. Now, why is that important? Well, the amount of intermolecular forces at play or present affects things like boiling point and melting point. So let's say you have a group of nonpolar molecules. Let's say you have C2H4, C3H8. and then like C4H10. We know these are all nonpolar because they're just carbon-hydrogen molecules, okay, with carbon-carbon bonds and carbon-hydrogen bonds. So which one is going to have larger surface area? Well, obviously, the bigger a molecule is, the more surface area it will have. So this one has larger surface area. And so it's going to have the highest boiling point because a molecule like C4H10 is going to have more London dispersion or van der Waals forces than a molecule of C2H4. So this one will have the highest boiling point. And this one would have the lowest boiling point. Does that make sense? So I think you're asked to do that on the homework, like order these molecules by their boiling points or melting points, increasing or decreasing. All right, questions on van der Waals. So that was one. The next one was dipole, dipole.
Okay, so if you have different molecules, how would you figure out the boiling point?
There are ways, but I'm not going to do something like that on the exam. Yeah. You'd have to have a little more knowledge than just what we talked about now. But I would do something like this where the molecules are all the same kind of atoms. So you can simply strictly tell by differences in surface area by the size of the molecule. All right, so dipole-dipole interactions are stronger than van der Waals forces. And these are the dominant intermolecular force in polar. Actually, I should say they are dominant in polar molecules that cannot hydrogen bond. So before you say, oh, the strongest intermolecular force for this molecule is dipole-dipole, make sure it cannot hydrogen bond. Any molecule that can hydrogen bond can experience dipole interactions, but it can also hydrogen bond, right? So the strongest would be hydrogen bonding. But for molecules that don't have a donor and an acceptor, you would say dipole interactions are the strongest. So what does that kind of look like? If you remember from the slide, the lecture slide, if you've got like two molecules next to each other, and dipole or dipole interactions, these occur in polar molecules. So when you have a polar molecule, you've got like a partial negative on one pole of the molecule and you got a partial positive on the other. There's a separation of charge. And it's because you have the positive and the negative poles of different molecules lined up, you get some sort of like interaction between those two. And that's what we call the dipole interaction. Okay. I think that's it for dipole interactions. Again, look at size. Okay, so if you have, we had an example. I want to say it was like C4H10, and then like I forget the example. It was like C3H something with O something. It was like acetone, and they had the same molecular weight, so they were the same size, but one was polar and one wasn't, and that you could see the difference in boiling point or melting points for those molecules. Okay, so if you have two molecules that are the same size, then you need to see, okay, which one is polar, which one's non-polar. The one that's polar can experience dipole interactions. It would take more energy to break apart molecules that are held together by dipoles than van der Waals forces. So we would say this one had a higher boiling point because of that. Okay, does that make sense? Okay, hydrogen bonding. So here, there are two, this one's the strongest, by the way. And there are two requirements. One, you have to have a donor. So that is a positively polarized hydrogen. Often, the moment you see a hydrogen bonded to an oxygen, nitrogen, or fluorine, you know it's positively polarized. But there are also other ways to get positively polarized hydrogens. You need an electronegativity chart probably to look and calculate the difference in electronegativity. But if you calculate it, it's 0.5 or greater, then you have a hydrogen that's positively polarized. All right, and then you also have to have an acceptor. And that is a lone pair on any oxygen, nitrogen, or fluorine. Okay, the lone pairs there are what we consider to be the acceptor. Software update. All right. Got to have both. So if you have one or the other, you could hydrogen bond with another molecule that could provide the missing piece. If you have both donor and acceptor on the same molecule, it can hydrogen bond in pure form with another molecule of itself, like a molecule of ammonia, NH3, has the lone pair and positively polarized hydrogens, donor and acceptor. Okay. I think that's it for the intermolecular forces. Next, we get to gas laws. So here, the two main laws I wanted you to remember was one, the combined gas law. And this was P1 V1 over T1 equals P2 V2 over T2. So how do I know when I'm supposed to use the combined gas law? Problems in which you need to use a combined gas law will say, hey, you've got this gas, blah, 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 and it will not say anything about moles, nothing about moles. Okay, or grams of a gas, because you have a homework problem that says you have 2.8 or 3.1 or whatever grams of propane, C3H8. Do you remember have y'all looked at chapter 8 homework? I think it's number 19. I keep getting questions about this one. It doesn't say you have a certain amount of moles of gas, but it says you've got like 5 grams of a gas. It tells you what gas. You can easily get the molar mass and convert that number of grams to moles. Okay, so on that one, you need to use ideal gas law. It gives you an amount of a gas. On this, you have nothing about moles, okay, or grams of gas. You have no way to know what quantity of gas you have. You're simply looking at changes in pressure, volume, and temperature. Okay, so that's when you know to use a combined gas law. Also, you need to make sure before you just plug things in and calculate something, you always have to rearrange the equation for the variable that you are solving for. If it's like T2 or P1 or whatever, isolate that term and then make units match. Okay, what I mean by that is like the units on P1, whatever that pressure, if it's ATM or PSI, that needs to match the units on the other pressure term if it gives you both pressures. So if you got PSI and ATMs, you can't plug both those numbers in without converting one or the other first. Same thing, volume. If you've got milliliters and liters, that won't work. You got to have both liters or both in milliliters. And then temperature has to be in Kelvin. So if you're given any sort of Celsius, you got to convert it to Kelvin. I didn't leave much room for, I'm going to try to shrink this down. I did not leave much room for the ideal gas law. All right, the last one is the ideal gas law. Oh, I have a whole nother page down here. I didn't have to do all that. This one is PV equals nRT. Okay, so this is your pressure term. This is volume. This is the number of moles of gas. This is your constant. Remember what that is? It is 0.0821, and the units, there's a lot of units here. It's liters times ATM, moles times Kelvin. And these units, I'm going to highlight them. They're critical, okay? They tell you the kinds of units you need to have on all the other terms. So like your pressure, because you got ATM and the gas constant, this better be in ATM when you plug it in. The volume better be in liters when you plug it in. Number of moles, obviously not grams. You can't plug in grams, you got to plug in moles. And then your temperature, which is the last thing we haven't labeled. This has got to be in Kelvin per usual, okay? Because everything needs to match R. So here, how do I know when he's at ideal gas law? This has something about moles. Okay, so it's either asking you how many moles of gas and you're solving for moles, or it tells you you got 2 moles of gas, or you have 10 grams of gas. Okay, if it gives you some sort of quantity, something about moles or grams of gas. Gives you some sort of quantity of gas, it tells you what gas it is, you can solve for moles and you could plug that in and use the ideal gas law that way. Okay. All right. That's kind of it for the summary. Any questions there on any of these things before we just switch over and start working problems? Okay. Well, we're going to start then. Go back to the first slide, Maria. Yeah. This one or the one down below? Okay. So we're actually going to start with a problem from like chapter 7 stuff, because it has a lot to do with the lab. That Le Chatelier's principal lab, I kept getting questions about exothermic and endothermic, like how do you tell? So we're going to review a question like that really quick and then jump into some chapter 8 stuff. Is that good, Maria? Okay. So this says predict the effects of decreasing the temperature on the position of equilibria, following equilibrium. So you got 3 equations here. And here's what we're doing. We're decreasing temperature. So let's look at A. I'm going to zoom in. We got hydrogen gas and chlorine gas makes HCl, and look, plus it makes 49.7 kilojoules of energy. Here, energy or heat is a product. So is this exothermic or endothermic? Keyshawn said it. Lucas said it. Exothermic, okay? What we're doing is we're decreasing temperature. Okay, so that's the initial thing that we're doing. We're decreasing temperature. So I don't know, it makes better sense to people different ways. If you want to think of the balance scale analogy, we're removing some weight off the product side. Okay, we're decreasing, you could say we're decreasing the concentration of heat because it's a product. So the scale, if you have a scale here, it's going to tip up because we're taking weight off the product side. It's going to tip up. So Le Chatelier's principle says we want to get the scales balanced again. So which side do we need to add weight to? Which side is the equilibrium going to shift to? Which way? Left or right? Okay, Maddie says left. Maria says right. Pernille says right. Here's what you can know. Anytime you take something away, anytime you decrease, remove, it shifts, equilibrium shifts towards that thing. That's okay, Maddie. So equilibrium is going to shift towards the side with temperature or heat on it. That makes sense? It's exactly what you saw for your equations. Both of those reactions, by the way, from lab were exothermic. Heat was a product. So that's why the first one, when you put it in the cold bath, it turned pink. Pink was the color of the product side. So when you put it in the cold bath and removed heat, it turned pink. It shifted towards the side that heat was on. If you increase the temperature, if you add heat, it shifts away from that side. Anytime you increase the concentration of something or add something to your reaction, equilibrium is going to shift towards the other side. Anytime you decrease or take away something, equilibrium shift towards that thing. That makes sense? I can't just say it's always going to shift left or always going to shift right because it depends what side heat is on. It depends what side the compound is on that you're manipulating. All right, let me. All right, so that one's going to shift towards the product side. It's going to shift right. Okay, B. You've got ammonia breaking down into nitrogen, hydrogen gas. Look at your delta H. It's positive, so this is endothermic. So is heat a product or a reactant? Yes, so you could write heat plus ammonia. So if we're, again, decreasing temperature, now which way is equilibrium going to shift? Yep, Purnell's got it. It's going to shift, again, towards the thing you're taking away. It always shifts toward, if you're taking something away or decreasing something, it shifts towards that thing. All right, you got another negative delta H on C. So you could write plus heat on the product side. You're decreasing temperature. Which way is equilibrium going to shift? This should be the exact same as A, right? In A, we had heat on the product side. So it should shift right again. Okay, does this help clarify? I think I got a lot of emails about this part of the lab over the weekend. So that's why I wanted to do this one. Any questions on this?
Are we going to get any questions about spectator ions on the exam?
I'm not really going to answer direct questions like that. I mean, anything that's from the labs or from the lectures is fair game. So did you understand those questions, Pernille? Like which one's a spectator ion and which one's not?
No, I didn't understand it.
Let's go over it so that you do understand it in case it is on the exam. So let's say, I think the equation was this. You had acetic acid. Makes H3O plus and C2H3O2 minus. All right, this was the equation from lab, the one that was the yellow and the orange and red. So you added sodium acetate, which is this. Okay, that's what you added to your test tube. Now this is aqueous. If you remember solubility rules, anything that has sodium in it is going to disassociate, it's going to be soluble. So it breaks up into these ions. That's what aqueous means. It dissolves into its ions. So the lab asked you which one's a spectator and which one can affect or can shift equilibrium. So you need to ask yourself, which one's in my reaction? Which one is present in the reaction itself? Is it sodium or is it acetate? What do y'all think? Yep, acetate. We got acetate right here. So this one can shift equilibrium. Sodium is in the test tube, sure, because you put it in there. But it's just sitting there watching. It's a spectator, okay? Just like a spectator at a ball game. Sure, you're at the game, but you're not in the game, okay? Sodium was in the test tube, but not in the reaction. Does that make sense? It has no power to affect your equilibrium. You can increase or decrease it all you want. It's not going to shift equilibrium. Now, acetate, on the other hand, you increase or decrease that, you'll shift equilibrium all kinds of ways. Does that make sense? Does that clarify? Okay. Good deal. All right. Next one. Okay, I want you guys to read this problem. It says the gases in a hairspray can are at a temperature of 27 degrees Celsius, so roughly a little more than room temperature, and a pressure of 30 psi, so pressurized, which is good because you want the hairspray to come out. If the gases in the can reach a pressure of 90 psi, the can will explode. What temperature must the gases be raised to in order for the can to explode? Assume constant volume. So a hairspray can, the volume of the can is not changing, so constant volume. How do we know what equation we need to use here? Do we use the combined gas law or the ideal gas law? I'm listening, I just gotta plug this up. Yeah, combined gas law, okay. Constant volume, we don't have anything about moles or grams of gas here. So, we got P1 V1 over T1 equals P2 V2 over T2. Have to remind myself about hairspray. I couldn't tell you last time I bought a can of hairspray. Do people still buy hairspray? We're not in the 80s anymore. All right. What are some things we need to do? First of all, what are we solving for? I'm going to highlight that. It says, to what temperature must the gas be raised in order for the can? So we're given an initial temperature. That's up here. I like to go through, remember, and annotate my problem. This is the first temperature, so I call it T1. So what we're solving for is T2. We don't know T2. And then we're given two different pressures. So pressure 1 and pressure 2. This is P1 and this is P2. So constant volume, we're just going to take volume out of the equation. So just literally erase it or whatever, mark it out. And here's what I noticed. What we're solving for is T2. It's something that's in the bottom on the denominator on that side of the equation, the right side. So what do we need to do to solve for T2? There's a long way or a short way. Okay, let's let you flip. You could cross multiply both sides by T2 and then cross divide both sides by P1 and cross multiply by, and move everything around, or you just flip the equation. It's a little easier this way. And then just cross multiply. Well, cross multiply both sides by P2. Okay. So my equation, excuse me, becomes, let me zoom in, P2 times T1 over P1 equals T2. There we go. Now the last thing we need to do is what? Can we just plug everything in now? Whitney said it. We need to convert this temperature up here to Kelvin. 27 degrees Celsius plus 273.15 equals 300.15 Kelvin. Now we can plug everything in because look, I've got PSI for both my pressure terms, so that's good. If you had like ATM on one or millimeters of mercury, PSI on the other, or pascals or something, then you'd have to convert. Okay, so just plug it all in. P2, which is 90 PSI, times T1, which is 300.15 Kelvin, divided by 30 PSI equals T2. Anybody can help me out with this? What do you get? Maddie got 900.45 P, oh, or temperature here. This is Kelvin. Okay, because PSI cancel out. Good, Grayson got the same thing. Okay, any questions on this right here? All right. We'll look at another problem. I'll kind of leave that visible while I read the problem down below. It says rank the following molecules in order of increasing boiling point. So you got 3 different molecules here, and all you need to decide is, 1, do these have different types of intermolecular forces? If they all have different types, it should be pretty easy to arrange them. Molecules that are nonpolar and have, the London dispersion or van der Waals, those will have the lowest boiling point. Molecules like in hydrogen bond will have the highest boiling point. Molecules in between dipolar that are polar molecules, they'll have in between boiling points. So what do you think about N2? Polar, nonpolar? Can a hydrogen bond with itself in pure form? I know you got a nitrogen with a lone pair there, but I should mention that. I should reword this question, say in pure form. Matt says London dispersion. So here's what nitrogen looks like. You got 2 identical atoms bonded together. This is nonpolar. The electronegativity difference is 0. So London dispersion or van der Waals. I'm going to write VDW, van der Waals. Or London dispersion is fine. HCN, what do y'all think about this molecule? Here's what HCN looks like. Now you might want to, there will be electronegativity chart on the resources page for exam 3. Here's what I know. I know hydrogen carbon bonds are always non-polar. And if you do look at electronegativity chart, the carbon nitrogen bond is polar. And you calculate the difference. So you can assign a partial negative to nitrogen and partial positive to carbon, and you can draw in a dipole. So this should be dipole. Dipole-dipole interactions because it's polar. Okay, what about CH3COOH? You draw the Lewis structure. You gotta have one of these oxygens double bonded, and then you got an O and an H. Oops. Okay, what do y'all think about this? Nothing? Y'all don't think anything about this? Nice, is hydrogen bond. So you see a donor and an acceptor? I do. This is positively polarized. And then look, you got all these lone pairs on these oxygens within the same molecule. So here's your donor. And all these lone pairs, these are acceptors. So you got all that within the same molecule. So for sure, yeah, this can hydrogen bond. So how should we order these from lowest boiling point to highest? Should it be A is lowest? Yeah, A, B, C. They're already in order. All right, A, B, C. A is the lowest, B is middle, C is highest. Questions on that? Okay, next problem here. How many moles of a gas? Oh, I'm gonna go ahead and highlight. Look, it's asking about moles of a gas. So what problem or what equation will we need to use? Yep, Matt said it, ideal gas law. PV equals nRT. How many moles of a gas does it take to occupy 120 liters at a pressure of 2.3 atm? and a temperature of 340 Kelvin. So here's our volume, there's our pressure, and there's our temperature. We're solving for N, okay? So we need to isolate N. So how do we do that? Should cross divide both sides by R and T. Yep, Maddie said it. PV over RT. So they cancel out over here. So you just have PV over RT equals N. Now, we've rearranged our equation. 2, the second thing you do, check. Do we need to convert anything? Like, do we have a Celsius and need to convert to Kelvin? Or do we have the wrong, remember, how do you decide what units you need? Look at ours, 0.0821. The units are liters times ATM, mole times Kelvin on the bottom. So do we have liters, ATMs, and Kelvin? Because we're solving for mole. If we do, then we can just plug everything in. And we do, liters, ATM, Kelvin. So we've got 2.3 ATM, that's the pressure, times the volume, which is 120 liters. On the bottom, we're gonna plug in R. I like to put this all in brackets. And then that's times the temperature. All of that equals N, number of moles. Yeah, Claire, I meant to get that up this weekend, but didn't happen. But it won't take me but a minute. Once this is over, I'll do it. Anybody get the answer? 2.3 times 120? So like 280 or something, divided by 0.0821 times 340. Grant said 9.89 moles. Yeah, units of moles there because everything, ATMs cancel, liters cancel, Kelvin cancels, except for moles. Okay, any questions on that problem? Here's another problem. It says I have 50-liter container, holds 45 moles. Oh, I've got moles in my problem, moles of gas. At a temperature of 200 degrees Celsius, what's the pressure inside the container? So because, again, it's giving you moles of gas or asking for moles, then we're using the ideal gas law. PV equals nRT. But this time we're solving for pressure. So how do we rearrange our equation? Yep, cross divide by V. So V cancels. So you get P equals nRT over V. All right, now do we need to convert anything? We've got liters for volume, so that's good. We've got moles for gas. Now, if I said you had 200 grams of a gas, and I said it's helium gas, all you need to do is take the molar mass of helium, looking at the periodic table, convert to moles, okay? But we do have Celsius for our temperature, so we do need to convert that to Kelvin. Everything else should be good to go. So now we just plug everything in. 45 moles, because you got N times R, which is 0.0821. I would have R handy somewhere, write it on a sticky note, or have that page of your lecture available. times T, which is 473.15 Kelvin, and divide all of that by V, which is 50 liters. And this equal, not N, we were solving for N last time. This equals P. Guys, I don't know what's going on in my throat. This thing will not go away. Moles, Kelvin cancels. Got liters up top, liters on bottom. Everything cancels but ATM. So 45 times 0.0821 times 473.15 divided that by 50. What do you get? Maddie says pressure is 34.9 ATM. And then if I ask you, how many pascals is this? Or how many, whatever, you could easily convert that, right? That should not be any big deal. And if the question doesn't say convert at the end, but it just says what's the pressure in pascals, you should know to solve for it and get the answer in ATM first and then convert. Okay, no big deal. Okay, how much do I got left? I got 2 problems left. That's it, because we're already at 10:44. So we'll work these last 2, and then if anybody has any questions, we're getting close to time. Got a lot of cans and fires. I was telling the morning session, this says it's not safe to put aerosol canisters in a campfire. So believe it or not, my husband, he does a lot with like woodworking. He loves like build tables and stuff. And so he has a lot of different like finishes and stuff or stains or whatever he does with the wood. And he will throw anything into a campfire. Styrofoam, canisters left over from whatever. It like freaks me out really bad. I tell him he's only allowed to burn like untreated wood, but he doesn't listen. It's a point of tension in our marriage. But clearly, if he would just read this, it's not safe to put aerosol canisters. He doesn't put aerosol, okay, but he'll put anything else almost in a campfire because the pressure inside the canisters gets very high and they can explode. If I have 1 liter canister, it holds 2 moles of a gas. The campfire temperature is, look at that, 1400 degrees Celsius. I had to look that up because I was like, is that a real thing? And it's a real thing. It can get that hot depending on the flame. What is the pressure inside the canister? So what law are we using? Anything look familiar? Yeah, this is pretty much the exact same problem as the one we just solved. You notice that? Look, it gives you moles of a gas. We got temperature in Kelvin, so we got to convert that, and it's asking for the pressure again. What is the pressure? So same exact equation as above. P equals nRT divided by V. Once you rearrange, got to convert temperature. So you do 1400 degrees Celsius plus 273.15, and you get, 673.15 Kelvin. And then you have liters and you have moles, so you're good. So then you just plug it all in. P equals 2 moles times 0.0821 times the temperature, 1673.15 Kelvin, and divide all of that by 1. That's nice. So 2 times 0.0821 times 1673.15. Okay, Maddie and Grant both got the same thing. Pressure is really high, 274.73 ATM. I literally tell them, like, you're going to get cancer if you burn that, like, which is probably a terrible thing to say, but it bugs me. All right, any questions on this problem? We got 1 left, and then we're done. At least this is all I had planned for the review. It was a lot of practice with gas laws. It seems like we're doing a ton of ideal gas law. Sorry, I would have picked more of the other laws. If I'd read more closely. Okay, how many moles of a gas are in a 30-liter scuba canister? Anybody been scuba diving before? I've always wanted to go. I've never been. 300 Kelvin, pressure of 152,000 millimeters mercury. So because we have moles, again, this is one more ideal gas law problem. PV equals nRT. Here's what I noticed. My volume has units of liters. My temperature, how do I know that's temperature? It's units of Kelvin. But pressure, what do you notice? Millimeters mercury. We cannot plug that number in. What do we have to do? Lucas, you're 2 steps ahead. So we got to convert this to ATM. We have to get pressure in units of ATM. So it's 152,000 millimeters mercury. I want to cancel units millimeter mercury and I want to convert to 8. So we need the relationship between millimeter mercury, ATM. So you have that slide from lectures. Let me show you which slide I'm talking about. It was up above the gas laws. Right here. This is the one. So you go find that slide and it tells you the relationship between millimeter mercury and ATM. So yeah, we're going to divide by 760. So how many ATM is this? Claire said 200. Because millimeter mercury cancels. Now we're ready to plug everything in. We are solving for moles again, so N. So we're going to divide both sides by RT, rearrange our equation. R and T cancel. So N equals PV over RT. So P is 200. V is 30 liters. When you have multiple things on the bottom, put it in parentheses, 0.0821. And then your temperature is 300. Please, if you have a file response question on these, you've got to show all your units. That's going to be a really big deal to me for points. Okay, how many moles of a gas are in this scuba canister? $200 times 30 divided by R and T. 243.6 moles of gas. That should be plenty of gas for a scuba trip. Moles, forgot units of moles. Right? So that one was a little different because we did have to convert one of our like pressure terms to the right unit. If you had milliliters for volume, you'd have to convert that to liters, so on and so forth. So that kind of brings us to the end of the hour, pretty close at least. Are there any other questions on any of this stuff or any other questions from the homeworks? You guys
could you work the last question of the homework?
Let's see,
I can pull it up.
Which one is it? I got it right here. Is it number 22?
Yeah.
Oh, session expired. Hold on. Let me re-log into mastering. Chapter 8, homework. All right, here it is. 22 or question 65. And it is the one about, okay, if a 0.614, you might have different numbers. Mine says if a 0.614 gram sample of gas maintains pressure at 283 millimeters mercury when contained in a 1 liter flask at 0 degrees Celsius, what's the molar mass of the gas? Interesting. Let me go to my blank note. Here we go. Y'all can still see my iPad screen, right? So here's the information it gives us. It says we have 0.614 grams. And you don't know what gas it is. And then it gives us a pressure, which is 238 millimeters mercury. We've got volume is 1 liter. Temperature is 0 degrees Celsius, but we're gonna have to put that in Kelvin. I can already tell you, this has got to do with the ideal gas law. So 273.15 Kelvin. What is the molar mass? So what is molar mass? What are units for molar mass? Not AMU, not just grams. Keyshawn said it. It's grams per mole. It's the amount of grams of any gas for 1 mole of that gas. So we're looking for grams per mole. So look, we already have the grams. 0. At least you plug in the number it gives you on your problem. Sometimes, again, it changes these up. We just need to solve for moles. So we have volume, pressure, and temperature. We know R. What can we do? We just need how many moles this amount of grams weighs. And we'll just divide those and get the molar mass. So we just need to plug all this in the ideal gas law and solve for N. So kind of what we did just a lot of. N equals PV over RT. So you just plug all these in, solve for N. So it should be, oh, but wait, we got to convert this to ATM first. 7, which we actually just did a practice on too. So it should be like 0.4 ATM or around that. What do y'all get? 238 divided by 760. Point 3. So 0.3 times the volume, which is 1 liter, and then R and T on the bottom. Okay, what do we get? How many moles of gas is that? It's a great problem. 0.02 moles. And then you just plug that number right there. So molar mass is the grams of the gas divided by the moles of gas. So what's the molar mass of this one? 0.614 divided by 0.02. And Maddie said 30.7 gram per mole. That was a great problem. I like that problem. Did that make sense what we did? Gave you grams. We used the ideal gas law to solve for moles, and then we did grams divided by moles to get a gram per mole unit, which is the unit for any molar mass of any gas or anything. Any other questions?